So welcome dear students, welcome to one shot series for GATE 2023, and today we are going to discuss metal forming processes. So once again I would like to remind you that in this lecture series we are discussing important topics which we thought that for GATE 2023 these topics will be important. So it is not a complete syllabus, but the important one for GATE 2023. Okay, so these are my credentials, because some of you may be seeing only few lectures. I am gold medal in BTech because I am a university topper of AMU in the class of 1997. I am MTech and PhD from IIT Delhi, and between MTech and PhD I worked for engineering services for approximately 1.5 years. I am also a researcher, and as per Scopus data 2020 I am in the top 5% researcher in the world. Primarily I work in material characterization, metal forming, that area. Over Scopus, if you type my name, you will get close to 200 papers to tell you my area of research. And now for PW GATE we have a team. It is not driven by one person or two person. There's a team for mechanical. These are the team members of Drona. So every member is expert in his field. Like I say in every lecture that suppose somebody claims that I know everything and all mechanical, each and every subject of mechanical, he must be bluffing. Because as a researcher we know that it is impossible to have mastery in all the field. So expert of every field is with us. Now let us start metal forming process. This metal forming process is broadly divided into 3 categories. It's the first classification of metal forming process. First is a cold working. Cold working. There is one classification of metal forming process like bulk metal forming and the sheet metal forming. Bulk metal forming are like wire drawing, extrusion, forging, rolling. These processes are under bulk metal forming process. And the sheet metal forming processes are blanking, punching, stretching, deep drawing. This type of stuff is in sheet metal forming. So bulk metal forming and the sheet metal forming is the first classification. Now the second classification is based on the operating temperature. Second classification is based on the operating temperature. So when the operating temperature is less than 0.4 Tm, in other words, less than recrystallization temperature, that working is called cold working process. Generally the recrystallization temperature of any material is approximately 0.5 Tm. Recrystallization temperature of most of the material is approximately 0.5 Tm, where Tm is in Kelvin, where this temperature Tm is a melting point in Kelvin. It is very, very important. So for most of the material, the recrystallization temperature is approximately 0.5 Tm. Okay, na? So less than 0.4 Tm is the cold working process or cold forming process, and greater than 0.6 Tm is a hot working process. Okay, and when we are forming the material at the recrystallization temperature, approximately 0.4 to 0.6 Tm, it is called warm working. In some books, they say 0.3 to 0.5 Tm. Doesn't matter, because for some material, the recrystallization temperature is less. But in most of the standard books I'm talking about, it is between 0.4 to 0.6 Tm. Most of the standard books I'm talking about, okay now? So, in the cold forming, when you are metal working, for example, forging, wire drawing, rolling, at a temperature less than recrystallization temperature, there will be work hardening. There will be work hardening. So due to work hardening, cold formed product will be strong. Cold formed product will be strong. Why the cold formed product will be strong? Due to recrystallization of the material. Okay. And in hot forming, products will be weak. Why weak? Because there is no work hardening of the material. Now in hot working, after metal forming, when the temperature comes to room temperature, because after some time the temperature has to come to room temperature anyway. So you are working at elevated temperature, and after forming, when you bring down the temperature to room temperature, there will be shrinkage, because upon heating the material always expand. So upon working, when you cool down the temperature to room temperature, there will be shrinkage. So hot working, product will lose accuracy. And in cold working, the products will be accurate. So why the products will be accurate? Because there is no shrinkage. So products will be accurate. Now, in hot working, because the temperature is already very high, more than the recrystallization temperature is already very high. So at high temperature, work material will have a tendency to oxidize. So the surface of work, there will be oxidation, and due to oxidation, formed product will lose accuracy. Formed product will lose surface finish, because the oxides are just like a dust accumulated all around the workpiece, and blow wind, oxides will go away and it will produce a rough surface. So due to the formation of oxide, products will lose surface finish. Surface finish will be lost. But this problem is not here, so you will get good finish here. So we will get good finish in case of cold working. So if we see here, Every time cold working is having advantage. But there is a very, very important advantage of cold working. There is a very, very important advantage of cold working, hot working. There is something called mean flow stress. There is something called mean flow stress. What is a mean flow stress? Generally, in all the metal forming book, it is designated as sigma naught. It is designated as sigma naught. So mean flow stress is the pressure, average pressure. Mean flow stress is the average pressure at which the metal begins to deform. At which metal begins to deform and take the shape of die. So average pressure at which the material begins to deform is called mean flow stress or mean flow pressure. At high temperature, for most of the material, if you see the stress-strain diagram, for most of the materials, let us say this is the diagram at room temperature. And when we increase the temperature, diagram keep on shifting in this direction. By increasing the temperature, the diagram keep on shifting in this direction. So at high temperature, mean flow stresses will be low. At high temperature, mean flow stresses will be low. So because the mean flow stresses are low, lesser energy will be required in hot forming at high temperature. Because mean flow stresses are low, so lower energy will be required to deform the material in hot working. And in the cold working, the biggest disadvantage is high energy is required to deform the material. High energy is required to deform the material in cold forming. Okay. Now, warm forming, all the properties fall in between. In warm forming, all the properties fall in between cold forming or hot forming. Okay. So this is the first comparison I have given. But one more thing also you remember, that as far as the defects are concerned, in cold forming, probability of defects will be more. Because there is a dislocation pile up, within the material, and wherever there is an excessive dislocation pile up, it may lead to the internal cracks. Wherever there is an excessive dislocation pile up, it will lead to the internal cracks. So if it is a defects like internal cracks, surface cracks, it is due to cold working. Hot working, there are some peculiar type of defects like barreling in forging, where we have gradients of mean flow stresses. So hot forming, the defects are slightly different, but majority of the defects are due to cold working, different types of cracks. In summary, you can say, as far as the defects are concerned, in the hot forming, primarily defects are two. One, due to variable mean flow stresses, and number two, due to high friction. Higher the temperature, friction will be more. Higher is the temperature, friction will be more. So because of high friction, we get defects like bamboo defect and barreling defect. But apart from these two, most of the defects are due to cold working. So here I have given the classification of hot working, warm working, and cold working. Now in the previous slide I have given you, the stress strain diagram, that upon increasing the temperature, how the stress strain diagram decreases in the downward direction. But here I would like to tell you certain things, that in the work material, if there is an impurity of chromium, the effect will be different. Upon increasing the temperature, effect on stress strain diagram will be different. So let us say at room temperature, this is the curve. Now 250 degrees centigrade, let us say this. If there is a chromium, something will happen between 300 to 650 degrees centigrade. Something will happen between 300 to 650 degrees centigrade. So what will happen? The stress strain curve will move in the upward direction like this. 450 degrees centigrade, 500 degrees centigrade, and at a certain temperature, the stress strain curve will be above room temperature, meaning all the temperature is increasing, but the strength of material will be higher than even at room temperature. This phenomena will happen in most of the materials where the chromium is present as a major alloying impurity. So what is exactly happening in the material? That in a certain temperature band, at a certain temperature band, mobility of chromium becomes more than the mobility of dislocation. Mobility of chromium becomes more than the dislocation. Mobility of chromium becomes more than the mobility of dislocation. So dislocation is moving peacefully. So from the backside, chromium comes and bangs the dislocation. So as a result of that, dislocation breaks into many parts. So suddenly the dislocation density increases, and when the dislocation density increases, strength will increase. When the dislocation density increases, strength will increase. This phenomena is called dynamic strain regime. Dynamic strain regime, or it is also called blue brittle region. And in this region, dislocation density will be high, and as a result of that, mean flow pressure will increase. So in forming, we have to be very careful. In metal forming, we have to be very, very careful that if chromium is present as an impurity, for example, different types of stainless steel, austenitic stainless steel, if there is a chromium, for hot forming, we have to avoid this range. We have to avoid the dynamic strain region from the material. You cannot form. If you try to form during the DSR region, dynamic strain region, material will fail in the brittle way. When you try to form during dynamic strain regime, material will fail in a brittle way. So of course, hot forming always decreases the forming pressure, but not always. So you have to be very, very careful when chromium is present as an impurity. Chromium is present as an impurity. Okay? So that was the introduction and comparison. Introduction and comparison. Now, I have introduced one term, mean flow stress or pressure. Because most of the students are having confusion here. So I will spend some time here. Okay, now I will spend some time. Generally, in most of the forming books, we designate by sigma naught. We designate by sigma naught. You can say that average pressure at which metal is deforming, average pressure at which the material is deforming and taking the shape of die. Now, case 1. I will be little slow here because I want everyone to understand this fundamental. Those who are watching this video, it is going in the recorded one. In exam, when only the yield strength of the material is given, indirectly the examiner is telling the material is behaving elastic and plastic. See very, very carefully. When only the yield strength of the material is given, it means indirectly question is telling you that it's an elastic plastic region. So sigma naught is equals to the yield strength of the material. See, in all the formulas of metal forming, wherever there is a sigma naught, put is equals to yield strength and go ahead with the solution. Okay. Case 2. In the question, if the yield strength and ultimate tensile strength, are given to you, it means the stress strain curve is elastic and the linear work hardening. elastic and linear work hardening. So indirectly, your stress strain curve is having linear work hardening characteristic. So here what we do, we calculate the average. Sigma naught is nothing but ys plus uts divided by 2. We will take the average. This is the average flow stress, and we will go ahead with the calculations. We will go ahead with the calculations. Okay. There is a case 3. Case 3 is suppose work hardening exponent and strength coefficients are given to you. Flow curve equation in the plastic region is sigma f is equals to k epsilon raised to power n MPa. When the complete flow curve equation is given to you, then we calculate the average. I am not going to go through the complete procedure in the one-shot series, because if you do the complete course, forming itself will take around 20 to 25 hours. So complete thing is not possible. You take the average by taking the element d epsilon, and the sigma naught is the mean flow stress. It will be k epsilon raised to power n over n plus 1. There is a proof for this. In the regular batch we have done it. There is a proof for this. When the complete flow curve equation is given to you, we will calculate the average, and this formula we will be using for the calculation of average flow stress, except in case of forging. Except in forging. In forging, we use normally sigma naught is equals to k epsilon raised to power n. We do not calculate average in case of forging because there are two regions. Reason number 1, characteristic of compression curve, and the reason 2, forging is done momentarily, because when the hammer put the tuck, so metal flows. So it's a momentary contact and deformation, so we do not calculate the average. So kindly do not do mistake, and this chart should be in front of you, that which data is given, accordingly what will be my sigma naught. So it's a very, very important slide. Okay. Now I want to go through a very important derivation. This is your tensile test specimen. This proof is so important that there are high chances that almost every year you can expect question in GATE. That is the reason I am covering here. It is so important that almost every year you can expect question in GATE. Okay. So there is a gauge length L0, and the cross section area is A0. This is the gauge. You are applying load, let us say P. You are applying load P. So instantaneously, let us say L and A are length and cross section area at some instantaneous point. at some instantaneous point. Let us say L is the length of the gauge and A is the cross section area of the gauge. Here I am also not going to the procedure of this derivation. Flow stress is also called true stress. Sigma naught E plus 1 and epsilon is nothing but ln E plus 1. There is a proof, and in strength of materials also you do these proofs. In strength of materials also do this proof, but here also in my regular class, if you see the crash course that I have given in Hinglish, there also this I have done this proof. Okay. So, but I am not going to go through the details proof here. Sigma F is load divided by the instantaneous area. It's a true stress, is nothing but load divided by the instantaneous area. Correct, na? So I can say P is equals to sigma F into A. Okay. Now differentiate this. Differentiate this equation. Differentiate this. So dP by d epsilon with respect to epsilon. What is epsilon? True strain. Epsilon is a true strain. dP by d epsilon is nothing but sigma F dA by d epsilon plus A d sigma F by d epsilon. I have differentiated with respect to epsilon. Okay. Now let us say you have the stress strain curve. You have stress strain curve. You will be shocked to know that in the plastic region volume will be constant. In the elastic region volume will not be constant because we calculate the volumetric strains. We calculate the volumetric strains, but in the plastic region the way deformation is taking place is by the moment of dislocation. So between YS and UTS volume will be constant. Now in the once the neck formation takes place, volume again will not be constant because there is a void formation. At the point of neck there is a void formation, so again volume will not be constant. Okay. So elastic region is only 0.2% of the total elongation, let us say 35%. For most of the steel, generally the elongation is approximately 35%. So with respect to 35%, I can neglect 0.2%. What is the 0.2%? Elongation in the elastic region. So I can neglect. So primarily I want to focus on the plastic region. So volume is equals to A into L. Now differentiate this with respect to epsilon. Differentiate this with respect to epsilon. So because volume is constant, so this is 0. dA by d epsilon into L plus A dL by d epsilon. Is that okay now? Because I drink a lot of water, so in between I shall give you some 5 seconds break. Now what you do, Divide this equation by L. So dA by d epsilon plus A by L dL by d epsilon. Okay. Now, what is the definition of true strain? What is the definition of true strain? D epsilon is nothing but dL by L. That's the definition of true strain. Na? See, once again, whatever derivation and the nitty-gritty details that we are going through now, you should revise it. Once I teach in the class, you should also revise it. Because for GATE, this is one of the most important section. And always there will be a high probability, every year there is a high probability that the question may come from this section. Okay. So what is the definition of true strain? D epsilon is equals to dL by L. So if you see here, this will be 1, check. D epsilon is equals to dL by L. So that will be equal to 1. So I can say that dA by d epsilon is equals to minus A. Okay? Correct? Very, very important discussion for GATE. This, you put it in equation 2. This, you put it in equation 2. So you will get dP by d epsilon is minus sigma F into A plus A d sigma F by d epsilon. A d sigma F by d epsilon. Everybody's okay? All right. If you see the load versus true strain, anyway, if it is live class, it would have been really great actually, because many students are having different type of questions whenever I am going through this thing. Load versus true strain curve will be similar to sigma versus E curve. Sigma F versus epsilon curve will be different. Sigma F versus epsilon curve will be like this. So you should know the geometry of each and every curve. So P versus epsilon curve will also be like this. And it is UTS. Okay, na? Because dP by d epsilon is the slope, na? dP by d epsilon is the slope of P epsilon curve. That's what mathematics says. dP by d epsilon is the slope of P epsilon curve. So this line is parallel to X. So can I say at UTS dP by d epsilon is equals to 0? At UTS dP by d epsilon is equals to 0 because the slope is 0. So here I can say at UTS this factor is 0 minus sigma F A plus A d sigma F by d epsilon. A cancels out. So I can say d sigma F by d epsilon is equals to sigma F. Okay? I think everybody must be comfortable by this. We also know the flow curve equation sigma F is equals to K epsilon raised to power n, because here it's a d sigma F by d epsilon. So differentiate with respect to epsilon. So d sigma F by d epsilon is nothing but K n epsilon raised to power n minus 1. Now multiplied by epsilon divided by epsilon. N by epsilon K epsilon raised to power n. K epsilon raised to power n is again sigma F. So d sigma F by d epsilon is nothing but n by epsilon sigma F. So if you compare equation 4 and 5, if you compare equation 4 and equation 5, what we will get? N is equals to epsilon. So work hardening exponent at UTS, work hardening exponent at UTS is equal to the maximum true strain. Work hardening exponent is equals to the maximum true strain. It's a very, very important result. And whatever we discussed in last half an hour, you will find variety of questions in GATE. Variety of questions in GATE you will find. So some P by Q you can do on your own. Of course, we are also providing solutions. But you try on your own P by Q, then you will get an idea that how these questions are being asked. Okay? Is that okay? Now, wire drawing. Wire drawing. So we are only seeing the GATE stuff. In wire drawing, there is a die, and the die is like this. This is a die. There are 4 regions in the die, and I will speak about as we go along. This is the incoming material. Incoming material. What we do, that incoming material is either given a bend or twist to remove oxide from it, because generally this material, raw materials, are stored in open or even some stores, and it is lying there for months together before it can be processed. So we have to remove oxide, because if we don't remove oxide, these oxides during the deforming will percolate and settle at the center. Suppose this is the outgoing wire. In the outgoing wire, if the oxides are present on the surface, during forming, these oxides will percolate down and settles at the center. Settles at the center, creates a metallurgical weakness, and that leads to crack. Metallurgical weakness tends to crack, and this defect is called fishtailing or tailpipe or fishing or pipe. So how the center line cracking appears? How the center line cracking appears? Because of metallurgical weakness, accumulation of too many oxides at the center. So we need to remove them. So how to remove? Either given a twist or bend. In other words, pickling, in technical language, pickling. Now, after removing the oxide, the incoming wire is dipped into some lubricant. Lubricants are two types, liquid lubricant or solid lubricant. Liquid lubricants are oils, different types of oils, vegetable or mineral oils, soap solution. And some of the very, very prominent solid lubricants are graphite, aluminum powder, plastic, soap powder. Okay, na? These solid lubricants we primarily use for giving high reduction. Solid lubricants we use for high reduction. And liquid lubricants when we are using, when we want to give a smaller amount of reduction. So after pickling, the incoming material is dipped into lubricant. So what will happen? A layer will be deposited. A layer will be deposited over the surface of incoming material. Okay? Okay? Now, the incoming materials enter into the die, with the help of a tube. With the help of a tube. Now, if it is a live class, I generally spend some time. On discussing these things in detail. But because it is a recorded lecture, I will tell you directly what is the purpose of this tube. When I ask a student what is the purpose of this tube, mostly what answer they give, to keep the incoming material straight. That is not the purpose of this tube. That is not the purpose of this tube. What is the purpose of this tube? What is the purpose of this tube? Because a thin layer of lubricant sticks to the incoming material, This is the lubricant. So lubricant is also moving with the same velocity. Lubricant is also moving with the same velocity as that of incoming material. Lubricant is also moving with the same velocity as that of incoming material. Okay. So now, when the lubricants hit the bell section of the die, this portion is called bell section of the die. When the lubricant hits the bell section of the die, all its momentum will be lost. All its momentum will be lost. But you know, lubricant cannot spin like this. Lubricant cannot spin like this because there is a tube. Because momentum is lost. One way is lubricant can squeeze out like this. That is not possible because there is a tube. So the loss of momentum of lubricant converts into pressure. Loss of momentum of lubricant converts into pressure, and this pressure enables the lubricant to enter into the deformation zone. This pressure enables the lubricant to enter into the deformation zone. Is that okay now? It's very, very important. Suppose the lubricant is not able to enter into deformation zone properly. Suppose the lubricant is not able to enter into the deformation zone properly. For example, in case of solid lubricant. In case of solid lubricant, sometimes it is possible that flow of lubricant is not continuous. So now hear this sentence very carefully. In case of solid lubricant, this problem will happen. In some region, lubrication is not effective because it's a solid lubrication. In some region, lubrication is not effective, and in that region, friction will be high, and that friction produces surface cracks. Surface cracks, and this defect is called bamboo. That defect is called bamboo. So when the bamboo defect appears, what is the bamboo defect? Cracks on the surface. And why cracks on the surface appears? Because of improper lubrication. And generally this defect will be prominent when you are using solid lubricant. So that is the purpose of this tube. So initially in the bell section, deformations will be primarily on elastic. No plastic deformation happens in the bell section. This section is called approach section, and the plastic deformation will happen only in the approach section of the die. Plastic deformation will happen only in the approach section of the die, and this angle alpha is called semi-die angle. Alpha is called semi-die angle. It's the die angle of the approach section. Okay, and this is called die land. You know why we provide die land? Because suddenly if we increase the area after approach, these are the stress razors. These are the stress razors. Because of stress razors, die will break. So although by providing die land, you are introducing another friction surface, so the drawing force will increase. But still die lengths are required for die stability. Still die lengths are required for die stability. And the semi-die angle. And this is called relief. Relief. So diverging section at the exit. Divergent section at the exit is called relief. Why we provide relief? Why we provide relief? Because the moment you release the load, elastic strains will try to recover. Elastic strains will try to recover. Suppose you are applying the tensile load. The moment you remove the load, length will slightly decrease. You are applying compressive load. The forging, the moment you release the load, height will slightly increase. Height will slightly increase. Elastic recovery. So to accommodate elastic recovery, we provide little diverging section. If we do not provide diverging section, die exit will break. Die exit will break. Die exit will break. Of course, there is a great mathematics and theory on the background, but that thing I will not cover in the one shot. Okay, na? Otherwise, I don't want to touch any topic and go. Whatever topic I touch, I want to go do thorough. Okay, na? So let us see alpha. Alpha is the semi-die angle. Alpha is the semi-die angle. So forming load versus alpha, it goes like this. There will be some optimum semi-die angle. There will be some optimum semi-die angle at which forming load is minimum. There is an optimum semi-die angle at which forming load is minimum. So you know why this behavior? Initially, by increasing alpha, because total forming load is equal to the load required in plastic deformation, plus load required to overcome friction. Load required to overcome the friction. So for giving the same percentage reduction, whenever in the metal forming, whenever we use this term percentage reduction, it is always area. It is always area. So initial area minus final area divided by initial area into 100. Percentage reduction means always area. So for giving the same amount of reduction, energy required in plastic deformation is going to be same. But by increasing alpha, lesser energy is required. lesser energy is required to overcome the friction. Lesser energy is required to overcome the friction. So, forming load decreases. If you increase the semi-die angle initially, because the contact area is decreasing, lesser and lesser energy is required to overcome the friction. So overall forming load will decrease. Overall forming load will decrease. Now, after optimum value of semi-die angle, if you further increase the semi-die angle, forging load is increasing. What is the reason? Reason is because of dead metal zone. Dead metal zone. Now, what are the dead metal zone? I am going to explain now. Suppose these are the dies. In fluid mechanics, we study streamline and potential lines. We study streamlines and potential lines. Streamline and potential lines. So in fluid mechanics, what we say, at any point of time, flow is tangential to the streamlines. We have very good faculties in Dream Drona fluid mechanics. There are 3 people. There are champions in the fluid mechanics. At any point of time, flow is tangential to the streamline and normal to the potential lines. Similarly, in the metal flow, there are something called slip lines, alpha slip line and the beta slip line. At any point of time, metal flow is tangential to the alpha line and the normal to the beta line. It's exactly the same concept. So, when the semi-die angle increases, so slip line will go like this, alpha slip line will go like this. So when the semi-die angle exceeds beyond a certain value, there will be regions where no slip lines are appearing. And these regions are called dead metal zones. Dead metal zone. Dead metal zone means the material that is not moving along with the other material. Dead metal zone means the portion of material which is not moving along with the rest of the material. Dead. So this dead metal zone not only obstruct the flow of metal, dead metal zone not only obstruct the flow of metal, but also moves in the backward direction. Because of that reason, larger energy will be required to deform the material. So why the forming load increases? Because dead metal zone is creating obstacles. Dead metal zone is creating obstacles. Dead metal zone is creating obstacles. Okay? I hope everything is clear from your side. And I hope that sometime we will meet live also. Sometime we will meet live also to take care of your doubts. So it's a wire drawing. Analysis of wire drawing and extrusion is exactly same. Analysis of wire drawing and extrusion is exactly same. See, tube drawing, I am not going to get through it. Some information about the wire drawing and extrusion we have given in 𝐂𝐸𝐴. You can download. I think it's freely available for everyone. 𝐂𝐸𝐴. So you can study from there. And the purpose of this lecture is to basically last moment revision for GATE 2023 for English speaking world in India. Okay. So the tube drawing, that's the reason I'm not covering tube drawing. Civil services, IFS and engineering services. IES, civil services and Indian forest services. Last 2 years, practically every year they are asking question from tube drawing, analysis of tube drawing. So when I'm teaching in the regular course, because it will take a lot of time, starting from the scratch. So regular course I will be covering, or maybe we will also start some mains course later on. There also we will cover. Okay, na? Otherwise, one-to-one basis, I'm always available for discussion through PW Telegram channel. Extrusion. Extrusion. There are 4 types of extrusion processes. Forward extrusion. In forward extrusion, this is the billet. Extruded part comes out in this direction. And if you see the load displacement curve, like this, load versus displacement curve. So in the forward is also called direct extrusion. Forward extrusion is also called direct extrusion, in which the extruded part comes out in the same direction of the piston movement. Extruded part comes out in the same direction as that of the piston movement. It is called forward extrusion. Second is the backward or reverse. Backward or reverse extrusion. In the backward or reverse extrusion, die is in the piston itself. So the extruded part comes out in the reverse direction. Extruded part comes out in the reverse direction as that of piston movement. As that of piston movement. And the load displacement curve is, it's a horizontal line, it's an inclined line. Now, certainly the question comes, in which process more energy will be required to deform the material? In which process more energy will be required to deform the material? Answer will be forward extrusion. Because in the previous slide I told you, that total energy required in forming of any material, it's the summation of energy required in plastic deformation, and energy required to overcome the friction. Here in the forward extrusion, there is an additional friction surface. There is an additional friction surface. There is an interface between the billet and drum. There is a additional friction surface. So how much additional energy is required? How much additional energy is required to overcome the friction? Let us say D is the diameter of billet and L is the length of the billet. Let us say PF is not sigma F, let us say, that is better. Sigma F is the additional pressure required on piston. Sigma F is additional pressure required on the piston to overcome the billet friction. So sigma F into pi by 4 D square is the load, convert into load, is equals to K dash is the yield strength in shear. K dash is yield strength in shear, and what is the shear area? Pi D into L. Pi D into L. If you solve it, sigma F is equals to 4 K dash L divided by D. 4 K dash L divided by D, and K dash is the yield strength in shear, and because it's a plane strain case, K dash is equals to sigma naught by root 3. Sigma naught we have discussed approximately 1 hour back. What is sigma naught? Is the mean flow stress. Depending upon whatever data is given to me, accordingly I will calculate sigma naught. So K dash will be sigma naught by root 3. Now in the forward extrusion, why the curve is going down? Because as the extrusion process continues, length decreases. As the extrusion process continues, length decreases. So length decrease, sigma F will decrease. Length decrease, sigma F will decrease. So lesser overall energy will be required in deformation. That's the reason curve is going down. Okay. So in other words, this is the energy required to overcome the billet friction. Energy required to overcome the billet friction. So suppose this question appears in exam, very frequently asked question, objective type. In which process more energy will be required to deformation? Forward extrusion or backward extrusion? Answer will be forward extrusion. Answer will be forward extrusion. Please remember that. Okay, na? So forward extrusion, backward extrusion. There are 4 types of extrusion processes, and I have elaborated in detail about forward and backward extrusion. Third one is hydrostatic extrusion. Hydrostatic extrusion. In hydrostatic extrusion, punch doesn't come in physical contact with the billet. Punch doesn't come in physical contact with the billet. This is a billet. And this is the hydraulic fluid. So punch pressurizes the hydraulic fluid, and this hydraulic fluid pushes the billet out of die, pushes the billet out of die. Generally, you know, in metal forming, there are many Indian author books, and most of the books, they are wrong actually. I have, you know, what logic, and by reading those books, many coaching faculties, they are also teaching the wrong concept. But what they say, by hydraulic pressure, the cracks closes, and that increases the formability. That is not the reason. Answer comes from plasticity. There are hydrostatic and deviator components. Hydrostatic component and the deviator component. And by applying the hydrostatic pressure, hydrostatic component increases, and hydrostatic component increases, and that increases the ductility. There is a very beautiful concept of plasticity, and in the one-shot course, I don't want to get into it. So you just remember one thing here, that hydrostatic extrusion is meant to form brittle materials. Form brittle materials because hydrostatic pressure increases the ductility of the material. Remember this concept, not basically crack closing and all that. See, my production engineering book, I'm taking out the 4th edition, and Narosa will publish it. Narosa Publication House, they will publish, and maybe we are 4th edition. I'm adding 2 more chapters, additive manufacturing and automation, with the help of Bits Pilani, my student Bits Pilani professor. And we are planning that February 1st week, it should be in the market. Narosa Publications. And on metal forming, I'm writing another book, international edition, with one of my friend at IIT Kharagpur. So he's also a metal forming man because we are students of the same teacher at IIT Delhi. So with him, I have planned to take out international edition on metal forming. Let us see how it works, because book writing is a very tedious work. So hydrostatic extrusion, and finally impact extrusion. Impact extrusion. In impact extrusion, there is a die in this shape. Die in this shape. At the bottom of the die, there is a soft material. This soft material is also called slug, either plastic or lead or high temperature metal, some soft material. Now a heavy punch is allowed to fall over the soft material. A heavy punch is allowed to fall over the soft material. As a result of that, soft material flows in this clearance, and you will get a tube. you will get a tube. Collapsible tubes. Collapsible tubes are toothpaste tubes, medicine tube. We purchase medicine from the market. Na? Collapsible means when we press it, it remains pressed. So all these different types of collapsible tubes are manufactured by impact extrusion. Okay. Now, as far as the calculation is concerned, or you can say analysis for wire drawing and extrusion is exactly same. Wire drawing and extrusion is exactly same. There are empirical formulas. There are empirical formulas given by Johnson's equation. Empirical formulas given by the Johnson's equation. So for cold forming, sigma d is nothing but sigma naught A plus B ln R. R is called initial area over the final area, and if it is an extrusion process, it is called extrusion ratio. If it is an extrusion process, it is called extrusion ratio. A and B are called Johnson's constant. Sigma naught is the mean flow stress. Sigma d is called either drawing pressure or extrusion pressure or stress. So once again, calculation formula are same for extrusion and the wire drawing. The values of the Johnson's constant will be different from extrusion and the wire drawing. Now there are formulas for hot working. Sigma d is equals to K1 ln initial area over final area. K1 is called extrusion constant. And this extrusion constant is a function of temperature. Extrusion constant is a function of temperature. So in exam, when the extrusion constant value is given to you, use this formula. And if the Johnson's equations value are given to you, use the above formula. Okay, so you have to be little attentive while solving the questions in GATE. You have to be little attentive. Okay, so first is there are empirical formulas. Now there is a slab analysis. So here again, I'm going a very simple way. Let us say it's a wire drawing. In wire drawing, I'm pulling the material from the front. Let us say back pull is 0. So sigma d is nothing but sigma naught 1 plus B by B, 1 minus AF by AI raised to power B. B is mu cot alpha. AF is the final area, AI is the initial area. I will be using this formula to calculate the drawing pressure. So load will be how much? Sigma D into AF. That will be the drawing load. Okay. So that is your, once again, in one shot, I'm going short. Whatever, because there is no time for proofs and all that. In the regular course, we will get into the proofs and other discussion. But one shot, I don't want to, because unless and I'm live, so whatever doubt you are having, I am able to see the doubt and clarify. I will not get into any complications. Now, if it is a extrusion, extrusion, what I'm doing, I'm pressing material from the back so that it comes out of the die. So the boundary condition changed. Because of boundary condition, this will become reverse. So sigma D is nothing but sigma naught 1 plus B by B. This will be reverse. AI by AF raised to power B minus 1. So because AI will be greater than AF, so to make the quantity positive, I have written in the front. So almost same formula for extrusion, and we know that this is nothing but extrusion ratio. AI by AF is extrusion ratio, and B is nothing but mu cot alpha. So extrusion force will be nothing but sigma D into AI. To calculate the force, the sigma D or the pressure needs to be multiplied with whatever area you are applying that pressure. So in wire drawing, you are applying that pressure at the exit, and in the extrusion, you are applying pressure from the back. I mean that is at the entry. You will get the extrusion force. Correct, na? Is that correct? Now, sometime in the questions, friction is not given. Friction is not given, so it is 0. In the question, when the friction is not given, it is 0. If the friction is not given, it is 0. So that sigma D will be nothing but sigma naught ln AI by AF. Please remember that based on this formula, you will also find many questions in GATE. So sigma D is equals to sigma naught ln AI by AF. Another very frequently asked question is, how much is the maximum deformation? How much is the maximum deformation I can give to any material? How much is the maximum deformation I can give to any material? So suppose in the wire drawing, I am pulling the material from the front. So the moment sigma D is equals to sigma naught. The moment sigma D is equals to sigma naught, so when I am pulling the material from the die, material start breaking from the front. You cannot deform the material. This is called drawing limit. limit. So how much is the maximum deformation I can give to the material in the most idealistic condition? Put it here, sigma d is equals to sigma naught here. So 1 is equals to ln ai by af. Take antilog. ai by af is equals to ve. So the percentage reduction is nothing but ai minus af divided by ai into 100. So ai by af, no, ai, sorry, ai, sorry, ai, 1 minus af by ai into 100. Put the value here, 1 minus 1 by e into 100. If you solve this, comes out to be 63%. Comes out to be 63%. So in the most idealistic condition, maximum 63% reduction can be given to any material. In the most idealistic condition, maximum 63% reduction can be given to any material. Is that okay with everyone? So we have covered extrusion and wire drawing. So here also we would like to do some problems. And in the problems, what I will do, I will show the problem for 30 seconds or maximum 1 minute. And please digest it first of all, because when I directly keep solving problem, you will not be able to grasp anything. So after flashing the problem for some time, I will wait for at least 30 seconds, 1 minute, so that you can digest and write the data, then we will solve it. Because if it is live, I am asking answer from all of you. So it's a totally different mechanism, but that is not the case here, it's the recorded one. So let us start solving questions. Read the problem. It's a, you know why I have taken this? It's a gate problem, P by Q, because this problem clears a lot of fundamentals of yours. The flow curve equation of the material is given by where epsilon is the true strain, the Young's modulus of elasticity of the material is 200 GPa. A block of thickness 100 mm is compressed to 95 mm, and when the load is removed, the final dimension of the block in millimeter is. It's a forging operation. Once again, this particular question I have seen many videos by teachers, those who are teaching online, because offline, you know, what people are doing, we don't know. To be frank with you, in a private colleges, students, they don't have any knowledge. So in coaching, whatever teacher teaches, it's acceptable. But online, many people are watching. There will be problem if you teach wrong fundamentals. So I have seen this particular solution, many teachers handled very poorly. And that is not correct. In fact, some people given the answers wrong. Anyway, in metal forming, you have to understand sigma f is equals to k epsilon raised to power n. The true strain is calculated in the direction of applied load. Because it's a forging, so epsilon will be ln h1 by h2. So here I want to give you some funda. So for 2 minutes, everybody should look at the board. It's a very, very important funda I want to give you here. Let us say it is a wire drawing operation. So stresses are in tension. So my stress strain diagram will be like this. Stress strain diagram will be like this. So the moment you remove load, they may ask you, what is the final length? In wire drawing operation, the moment you remove the load, what is the final length? So let us say this is your sigma. The moment you remove the load, it will follow this line. These two lines will be parallel. These two lines will be parallel. It is called elastic recovery. So, last 10 years, such type of questions you will find three such type of questions appeared in GATE, and a very technical question. That is the reason I have incorporated this particular P by Q here. Otherwise, I do not like to have P by Q, but certain P by Qs are very, very beautiful, and every student should learn them. But now let us say it's a forging operation. So in forging operation, stresses are compressive in nature. It's a compressive. And that will appear in the forging. And when you remove the load, so let us say from here, these two lines will be parallel. And this is elastic recovery. In summary, forging, the moment you remove the load, height will slightly increase. Question is asking about that in what is the final height once you remove the load. If it is a wire drawing, the moment you remove the load, length will slightly decrease. What is that final length? So I'm giving you basically the solution. So epsilon ln h1 by h2, it is coming out to be, I'm giving directly solution because it is not live session, 0.051. Okay, na? And the sigma f value is given to you, k epsilon raised to power n, it will be 371.5 MPa. 371.5 MPa. Once again, you should have cool head while you are watching this particular recorded video. You should have a cool head. Cool head is very, very important. If the head is hot, you are going to make blunders. This Hooke's law, what is this? True stress. This is the true strain. This Hooke's law, Young's modulus is nothing but stress divided by strain. These are not true stresses. These are injuring stress and injuring strain. So this true stress convert into injuring stress. We know that epsilon is nothing but ln E plus 1 So from here you can find out E. And once E is found out, sigma F is equals to sigma E plus 1. This is the engineering stress. You can find out the sigma. So you find out sigma. Okay. In GATE exam, I hope you are head school. In GATE exam, if the time is less, because all the three, and I told you in last 10 years, such type of problem appears 3 times. In all the 3 times, this question was NAT. And this particular question range was very, very small. Whatever, I think this problem was set by IIT Bombay. The range was very small. So if you have paucity of time, you can assume that sigma F is equals to sigma. Of course, it is not correct, but you can apply this and go ahead with the solution. Okay. So let us say this strain is even. E and sigma. So sigma by E1 is equals to Young's modulus. How much is the Young's modulus given? 200. This is MPa, this is GPa. So GPa convert into MPa. So by that you calculate E1. Understand? I have given all the procedure. This E1 comes out to be 1.85 into 10 raised to power minus 3. This E1 comes out to be 1.85 10 raised to power minus 3. So what is this E1? dH by H. This H is 95 mm. Now this triangle is, the moment you remove load, initial height is now 95. What is the final height? For that calculation we are doing, first is from 100 to 95, first step. Second step is from 95 to what? So we know the strain, calculate DH. So final height is nothing but 95 plus DH. And that will be the answer, and the answer comes out to be 95.157. 95.157. So you know what I recommend to all of you, those who are seeing this recorded version, either you pause the video and do this calculation with the help of calculator and paper formally calculated. Otherwise, after watching this video, you solve this problem at least 2 times. Because based on the same theme, last 10 years, there are 3 questions. So very, very important question for, GATE examination. Very, very important question for GATE examination. Okay. This is also GATE exam question. Again, GATE paper. This point is C. Okay. Just 30 seconds. You please read the question properly. 30 seconds. Please read the question properly. Now here, apply Hooke's law in this triangle. Apply Hooke's law in this triangle. So can I say AC divided by BC is nothing but Young's modulus? AC divided by BC is Young's modulus. This is 500, this is 100. So AC is 400 divided by BC. And what is the Young's modulus given is 200 GPa. GPa converted into MPa. So calculate BC. Epsilon B is nothing but overall is 0.5 minus BC. This was also NAD 0.498. Answer is 0.498. 0.498. Okay. These are easy questions. Please see this question. It's a MSQ, multiple select question. It is multiple select question. All right. Cold forging results in improved quality due to which of the following? Cold working, whatever we discussed, it's a better mechanical properties of the process. Now, in the cold forming, grains will break. So, it is not unbroken grain flow. Grains will break. It is not unbroken grain flow. Grains will break because the dislocation pile up. Excessive dislocation pile up leads to fracture and the breaking of grain. So second statement is not correct. You will get a smoother finish. You will get a smoother finish because there is no oxide formation. There is no oxide formation, so we will get a smoother finish. Now high pressure. It is a very beautiful question. Of course, in cold working, high pressures are required to deform the material. But that is not the cause of improved quality, na? Question is saying improved quality. That is not cause of improved quality. So 1 and 3, A and C are correct. Suppose the question is twisted in this way. Suppose the question is twisted in this way that what is the characteristics of cold forging? Then it will be A1, 2, 1, 3 and 4. But the question is specific about the quality. Question is specific about quality. So high pressure cannot be the cause. Read the question for 30 seconds. Read the question for the 30 seconds. Consider the following statements. The material properties which principally determine how well a metal may be drawn are ratio of yield strength to the ultimate tensile strength. You know why? ys to UTS gives information about the work hardening exponent. And the work hardening exponent is a very important parameter. Work hardening exponent is a very important parameter in determining the formability of the material. Rate of increase of yield stress related to the progressive amount of cold work. Yeah, again it is telling the value of N in other terms. Rate of work hardening. All three are correct. All three are correct. This is the next question. Determine the value of the strength hardening exponent. We have to find out strength hardening exponent or work hardening exponent for a metal that will cause the average flow stress is 3/4 of final flow stress. 3/4 of final flow stress. So we have to find out the value of the work hardening exponent. So what is the mean flow stress? Is a K epsilon raised to power N over N plus 1, and this is sigma F. So we can write down sigma Fm is equals to sigma F divided by N plus 1. So put all these values here. Sigma Fm is 3/4 of sigma F is equals to sigma F over N plus 1. This will cancel out. You can find out N. So questions are always easy, but you should know the fundamental. And as I told you, that whatever derivation I did, that was one of the most important thing. Whatever derivation I did, that was one of the most important thing for gate. So value of work hardening exponent, if you solve, comes out to be 0.33. Value of work hardening exponent is 0.33. Okay. Now see the next one. This question is from Extrusion. So quite possible that some of you might have seen the crash course that is available on the YouTube. So there I have given one suggestion to the students. Whatever data is given, put in the diagram form. Put the entire data over the diagram, and then solution will be easy. So cylindrical billet that is 100 millimeter long, so keep on writing the data. 100 millimeter long and the 50 millimeter diameter, keep on writing the data. So over the diagram, when the data is there, solving the question will be very, very easy. Solving the question will be very, very easy. Is reduced by indirect backward extrusion to 20 millimeter diameter. So it's an indirect extrusion like this, and this diameter is a 20 millimeter. So I'm saying if it is a direct, it will be like this. Indirect means pressing from this side, extrusion part coming from that side. The diangle is 90 degree. Diangle 90 degree means semi-diangle alpha will be 45 degree. Semi-diangle alpha is 45 degree. The Johnson's equation has A is equals to 0.8, B is equals to 1.4. So Johnson's equation sigma D is equals to sigma naught A plus B ln R. And the flow curve of the work metal has a strength coefficient 800 and strength hardening exponent 0.13. 800 and 0.13. So flow curve equation is given to you. Determine extrusion ratio, true strain, ram pressure, and the ram force. So this is the data. Extrusion ratio is initial area over the final area. Initial area over the final area is the extrusion pressure. So pi by 4 50 square divided by pi by 4 20 square. Okay. Then the true strain. See, one more fundamental, I told you that we calculate the true strain or the strain, the direction in which we are applying the load. Like in forging, it is ln hi by hf. True strain or the engineering strain are calculated the direction in which you are applying the load. So here the direction in which we are applying the load is the length direction. So ln lf by li. So in the work hardening region or plastic region, volume is constant. So ai li is equals to af lf. So lf by li is equals to ai by af. So same thing can be written ln ai by af. True strain. And if you solve this, this is 1.83 and this is 6.25 and this is 6.25. Okay. Now third is basically extrusion pressure. Extrusion pressure. So for that you have to find out sigma naught. Sigma naught is k epsilon raised to power n over n plus 1. As I told you around 1.5 hours back, that except in case of forging, for other cases we calculate the average. Sigma naught, if the flow curve equation is given to you, sigma naught will always be k epsilon raised to power n over n plus 1. But for forging we will not do that because of two reasons I told you. Because of stress strain curve in the compression, and number two, forging process is done momentarily. Fraction of second it is over. So now put everything here, sigma d, sigma naught a 0.8 plus B ln 6.25, and the reinforce sigma d multiply the area on which the force is applied. So if you see, this is the area, see, this is the area, into pi by 4 50 square minus 20 square. Two 2578 MP is this. Two 578 MP is this. And the force is 4.25 meganewton. 4.25 meganewton. Okay. Correct, na? Most of you will be seeing the recorded one. That is the reason between the two problems I am giving 30-second 1-minute break, so that you can digest and simultaneously you can practice the problem, so that things are not accumulated. Okay, na? When the things are accumulated, you will never be able to do. You will never be able to do. This question, 50% of this question appeared in GATE, extrusion ratio. But from wherever the question was taken, shift factor was also asked. It is from one foreign book. Okay? From foreign book. Now, extrusion ratio definition will not change. It's the initial area divided by final area. The definition will not change. So this area, final area is nothing but 50 into 12 is this area, and 62 minus 12 is again 50. So this is also 50 into 12. Okay, so that is that area. And initial area is 100 millimeter square. Diameter, so pi by 4, 100 square. So initial area or the final area. So by that you can calculate the extrusion ratio. By that you will calculate the extrusion ratio. This question appeared in GATE, but from wherever this question was taken, there was a B option also, shift factor. There is a B question, shift factor. Okay. So the shift factor is extrusion pressure for a given shape, extrusion pressure for a given shape divided by extrusion pressure for a circular cross section. Circular cross section having same area. So whatever area you have, the same area if you convert into a circle, how much pressure will be required to extrude circle? And this L shape. L shape extrusion pressure divided by the circle extrusion pressure is called a Shreshth factor. It's called a Shreshth factor. So there is an empirical formula for that. To find out the forming load and other parameters, there are 5 approaches. Upper bound theorem, lower bound theorem, slip line field theory, slab analysis, and the empirical formulas given by Johnson. So for the Shreshth factor, there is an empirical formula is 0.98 plus 0.02 px by pc raised to power 2.25. What I recommend that you mug up this formula. It is not difficult to mug up this formula. Px is perimeter of extruded section For example, this is the L shape. So what is the perimeter? This is the perimeter of extruded section. So 12 plus 50 plus this much, how much? 38 plus 12 plus 50 plus 62 is called perimeter. Okay. And PC is the perimeter of circle having same area. Same area as extruded section. I mean, whatever section is extruded, this calculate the area. Here also we have calculated area. Equate it to the circle area, pi by 4 d square. D is the diameter of the circle. So PC will be pi d, perimeter of pi d. So Px is the perimeter of the extruded section, and PC is the perimeter of circle having the same area as that of extruded section. So put everything here. For your confirmation. This PC, because I have solved this thing, is 122.8 millimeter. And the Px is, I have directly put in the calculator. Px is 224 mm. Because I have solved this before teaching to you. So if you put everything there, Shreshth factor comes out to be 1.057. 1.057. Okay. Okay. All right. Purposefully, I am giving these small breaks so that you are with me. Because if it's a live session, I don't know how much you have done it, but it is going recorded. But doesn't matter. But doesn't matter. All the problems, all of your problems will be taken care of. Okay, na? All of your problems will be taken care of. Whatever doubt you have, you just let me know. For GATE 2023, another very important topic is rolling. Rolling. So, rolling in a nutshell, if you see, suppose these are the grains. There are systematic grains. Systematic grains. And now we are rolling the material. This theta is called bite angle. Theta is called bite angle, or the angle the deformation zone is making at the center. Angle that the deformation zone is making at the center is called bite angle. So during the deformation, what you can see that the grains are elongated. So you will get elongated grains. You will get elongated grains during rolling. Of course, if the rolling is done at room temperature, then because of excessive work hardening, grains will be finer and finer. See, recently somebody quoted me from one Indian author book that the rolling is always done at high temperature. It's a wrong statement. It's a wrong statement. That's the reason I told you that especially in the forming, avoid reading any book, follow my notes, or if you can follow Johnson and Miller, Engineering Plasticity by Johnson and Miller. That is a book I follow. If there is any issue, I want to cross check anything in the forming, I follow that book. Engineering Plasticity by Johnson and Miller, and it is freely available on internet. You can download. So elongated grains. Now there are certain very important things that we have to see in gate. Suppose these are the pair of rolls. Pair of rolls. And after rolling, material comes out like this. Let us say R is the roll radius, R is the roll radius, and crazy, theta is the bite angle. Software is behaving a little crazy way. Okay. So theta is the bite angle. Let us say H1 is the height of incoming material and H2 is the height of outgoing material. Incoming material and outgoing material. Okay. V1 is the velocity of incoming material and V2 is the velocity of outgoing material. Naturally, our common sense says, what I recommend to all of you, whatever I am going through in 45 minutes, whatever I am going through 45 minutes, you should pay very careful attention. And those students who are studying first time this rolling section, what I recommend, this 45-minute to 1 hour section, they should see 2 times. They should see 2 times. It's a very, very important topic for not only for GATE, but for other competitive examinations as well. So, our common sense is V2 will be greater than V1. Because the cross-section area is decreasing, we can apply continuity equation. Let us say the width of the work remains constant. So A1 V1 is equals to A2 V2. So we can apply the continuity equation. A1 V1 is equals to A2 V2. So velocity of roll velocity we can say pi dn by 60, pi dn by 60. Diameter of roll is a 2r. Diameter of roll is 2r. So Vr is the roll velocity, V1 is the velocity of incoming material, and V2 is the velocity of outgoing material. So this V2 will be greater than Vr, will be greater than V1. Okay. So in the deformation zone, there will be a section. In the deformation zone, there will be a section. In the deformation zone, there will be a section at which roll velocity is equals to the velocity of material. Roll velocity is equal to the velocity of the material. And this plane is called neutral plane. This plane is called a neutral plane. This plane is called neutral plane, okay? So velocity of deforming material keeps on increasing in this direction. So there will be a plane at which the roll velocity and the velocity of material becomes equal, and that plane is called neutral plane. In this region, velocity of work material is less than roll velocity. Velocity of work material is less than roll velocity, and so it is called lagging zone. And in the lagging zone, there is called backward slip. And the backward slip is nothing but V1 minus VR divided by VR into 100. Backward slip. Okay? And in this region, velocity of material is more than the roll velocity. Velocity of material is more than the roll velocity. It is called leading zone. Leading zone, there will be forward slip. And the forward slip is VR minus V2 divided by VR into 100. Leading zone, forward slip. Lagging zone, backward slip, bitangle. Please be careful what sentence I am going to tell you now. To roll any material, backward slip is required. See, I am able to move on this floor. You know what is the meaning? Between my feet and the floor, there is a backward friction. Between my foot and the floor, there is a backward friction. If there is no backward friction, I will not be able to walk. If there is no backward friction, I will not be able to walk. So here, let us say P is the load applied. Rolls are like dies. Because rolls are deforming the material, rolls are like dies. The lagging zone, I hope everybody is little carefully looking at the screen. So lagging zone, because its velocity is less than the roll velocity, lagging zone velocity is less than the roll velocity. So you are standing on the roll. And looking at the deformation zone. You are standing on the roll, looking at the deformation zone. So relatively, material is moving in the backward direction. Relatively, material is moving in the backward direction. So friction will be in the forward direction. Friction will be in the forward direction. Okay. But now same thing in the leading zone. Velocity of material is the roll velocity. Velocity of material is more than the roll velocity. So you are standing on the roll, looking at the deformation zone. Material is moving in the forward direction because the material velocity is more than the roll velocity. So friction will be in the backward direction. So you can say that Neutral plane is the plane. Neutral plane is the plane at which friction changes direction. Neutral plane is the plane at which friction changes direction. So, in this first slide of rolling, I have explained to you the basics of rolling. So, why the leading zone is required? Because in the leading zone, friction is in the backward direction. If there is no backward friction, I will not be able to walk, or in the rolling, roll will slip over the material without any deformation. Roll will slip over the material without any deformation. Okay? So, in gate, very easy problem comes. So, I am going through one small derivations, and if you focus on these derivations, I am 100% sure you will be able to hit every single problem of gate. Every single problem of gate. Theta is the bite angle, H1 and H2. Now see very carefully what I am doing. P is the load applied by roll over the work material. P is the load applied by the roll over the work material. Newton's action-reaction law. Newton's action-reaction law. Suppose you apply any force, that material will apply equal amount of force in the opposite direction. Newton action-reaction law. So, same amount of load will be applied by the work on the roll. Same amount of load will be applied by the work on the roll, and this load will try to deform the roll. This load P will try to deform the roll. That's the reason P is called roll separating force. Roll separating force. Okay. Now we have seen the friction direction in the previous slide. So this is P. This will be mu P. Correct, na? So this is theta. This will also be theta. Can I say it's a P sin theta? And this is the mu P cos theta. I am taking the component of P and mu P. I am just taking the component of P and mu P. Okay. So as long as mu P cos theta is greater than or equal to P sin theta, as long as mu P cos theta is greater than or equal to P sin theta, then what will happen? Material will be automatically drawn between the rolls. material will be automatically drawn between the rolls and the no external pressure is applied. Material is automatically drawn between the roll. This is called condition of self-entry. No external pressure is required and the material will be automatically drawn between the rolls. Condition of self-entry. So if you solve this, tan theta will be almost mu. So only this much maximum reduction you can give to the material for the condition of self-entry. Condition of self-entry means just put the material between the rolls, it will be automatically drawn. No external pressure is applied. But remember, beyond the condition of self-entry, also deformation can be given. I will speak on this after 2 minutes. So let us say make on this side, this is the theta. Can I say this is delta h by 2? Delta h is nothing but h1 minus h2. Delta h by 2, delta h by 2. Okay, na? All right. Now, this let us say O, A, B, C. This AB is called length of contact. In GATE exam, you have to be very, very careful what is being asked. So AB is called length of contact, and generally we say it's L. This AC is called arc of contact. AC is called arc of contact. Okay? Is that all right with everyone? If the question is asking about arc of contact, calculate AC. If the question is asking about length of contact, calculate L. This is the bite angle. So from triangle OAB, this is theta. Can I say tan theta is nothing but AB divided by R minus delta H by 2. This is R, this is delta H by 2. I can do that. And how to find out this L? See, there is one geometry, there is one rule of geometry. There is one rule of geometry. Suppose there is a circle and there are two perpendicular lines. There are two perpendicular. This is a rule of geometry. This into this is equals to this into this. This into this is equals to this into this. So in this case, this is L, this L. This is the delta H by 2. And this is 2R minus delta H by 2. So I can say L square is nothing but 2R minus delta H by 2. If I multiply inside, neglect delta H square compared to R delta H. So L will be R delta H. Okay, length of contact will be under R delta H. Put it here. So tan theta is mu under root R delta H divided by R, because delta H by 2 also can be neglected as compared to R. So here mu is equals to, if you solve this, delta H by R, and comes out to be delta H is equals to mu square R. Delta H will be mu square R. Now now I'm telling the story now, whatever I told you 2 minutes before. If this is the bite angle, tan theta is equals to mu, that comes out to be delta H is equals to mu square R. Delta H is called draft. Delta H is nothing but H minus H2. It is called draft. Draft. Now here what I'm saying, self-entry means when you put the workpiece between the roll, material will be automatically drawn, no pressure is applied at the entry. This is called condition of self-entry. Beyond the condition of self-entry also, deformation can be given to the material. Beyond the condition of self-entry also, deformation can be given to the material. But in that case, you have to apply external pressure. Because last 23 years I'm teaching these things, and every time students say, previously I used to talk offline, now online. I'm teaching since 2018. When a student asks, basically practically every year, sir, we are not able to visualize this. So every year I give the same example. Every year I give the same example. By the grace of God, you will be selected in GATE, and many of you will go to IITs, okay, na, for their post graduation or PhDs. In IIT, you will see a different system. Of course, in all the IITs, there are excellent teachers, especially IIT Delhi, IIT Bombay. My gurus are there, and my friends practically in every IIT as teachers. You will see a phenomena. These BTech people are brilliant because they are cracking JEE. They are brilliant, no doubt they are brilliant. But except in the semesters or mid-exam or major exam, nobody studies after classwork. Morning 8 to 5 there is a classwork. After that nobody studies. They are playing because they have studied for JEE and all that. Nobody studies. So after dinner and all that, they will play. They will play cricket in the wings, and they are in the enjoyment mood. 10% students they study, and in IITs they call them Maggu. Okay, 90% they enjoy their life. Of course, they are brilliant people. So this enjoyment goes on till 1 or 2 a.m. 1 or 2 a.m. because 7 years I spent in IIT Delhi, my MTech, engineering services. I went outside. Again, I came for PhD. So total 7 years I spent in IIT Delhi. So 2 o'clock they will study. To 2 o'clock they will sleep. Go to sleep. In IITs, unlike in other colleges, you cannot afford to miss the class. If the attendance falls short, you cannot do anything. You are failed in that particular subject. It's a very strict system, study-oriented system. So you have to attend class, and the class is at 8 o'clock. The boy slept at 2 o'clock. So he will get up at 7:30. Boop, oh, 7:30. So go to the bathroom, whether he has taken bath, forget about it. Go to the mess. What is their mess? Bread jam. So put bread jam. And from the hostel to the institute, generally it's a good 2-3 kilometers in most of the old IITs. So he will do, put the bread in the mouth and cycle, duk, 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 cycle is going. And the bread, automatically bread is going the mouth. And by the time institute comes, bread is in the stomach. This is the condition of self-entry. This is the condition of self-entry. Without any external force, bread is going in the mouth. Self-entry. Understood what is the self-entry? Now, when the same student comes from institute at 5 o'clock, and generally in the hostel area there is a cafeteria. In every IIT system is different. I think all of you should go to IIT to see that, basically enjoy the life and study. So there is a cafeteria, and the same student asks for burger, bun, or some tikki. It is a big thing. Now you have to push the burger in the mouth. Oh, you cannot take it on, mouth cannot take the burger on its own. So burger eating, we are beyond the condition of self-entry. I hope you enjoyed this example. So once again, beyond the condition of self-entry, external pressure needs to be applied to deform. But it is possible to deform. Is that okay with everyone? Is that okay with everyone? So whatever formula I am deriving, all of you should remember. And sometime in the GATE I have seen they are asking the question from intermediate steps. So that is the reason all of you should know how I have calculated all these things. How I have calculated all these things. Okay? So mugging approach is not good. Mugging approach is not good for GATE. Now again, this condition of self-entry, people likes anything like this. Actually, somehow it clicked in year 2000. This is the neutral plane. Now, if you see the friction hill, if you see the friction hill, similar to forging, here also there is a friction hill. So the friction hill is like this. Friction hill is like this. And the area of the friction hill, will give you the rolling load. So what is the rolling load? Area of the friction hill will give you rolling load. And this is sigma naught, mean flow stress. So actual calculation of rolling load is very complicated. Actual calculation of rolling load is very complicated. So how we do it? If you see per roll, this is the friction pressure applied. I am taking two big assumptions in the calculation of approximate rolling load. I am taking two big assumptions. First assumption is my friction hill my friction hill is rectangular. Friction hill is rectangular. So the area force is nothing but sigma naught W into L. W is the width of sheet. Width of sheet can be seen perpendicular to the plane of this board, and this is L, length of contact. Length of contact. Okay, so that is the force per roll. I am calculating per roll. Now, the second assumption that I'm making here is that the neutral plane is exactly in the middle. Neutral plane will never be in the middle. So it's a very big assumption that neutral plane is exactly in the middle of deformation. If that is the case, torque is equals to F into torque into F into L by 2. So the torque is known, you can calculate power per roll T into omega. Let us say N is the RPM of roll. So omega is 2 pi N by 60. So power per roll. And if there are 2 rolls, total power will be 2T omega. Don't forget to multiply it by 2 if there are 2 rolls. So based on whatever I have discussed here, every third year question appears in GATE. So here there are 2 big assumptions. Here there are 2 big assumptions in this analysis. First assumption is my friction hill is a rectangle. And the second assumption is that the neutral plane is acting exactly in the middle of the friction hill. Neutral plane acting exactly in the middle of friction hill. In the middle of friction hill. Okay, is that okay with everyone? Now, very important thing. This is your pair of rolls. Pair of rolls. And let us say this is H1, H2, and I discussed with you draft. Delta H is nothing but H1 minus H2. Draft delta H is nothing but H1 minus H2, and we have also discussed the friction hill. Let us say this is for the condition of self-entry. If I increase the value of delta H, you know what I have to do? I have to apply a compressive stress at the entry. Larger the value of delta H, more will be the value of sigma 1. So by this is sigma naught, and if you apply compressive stress at the entry, what will be the effect of sigma 1 on the friction hill? By increasing sigma 1, how the curve will shift like this. This is sigma 1. Curve will shift like this. Larger is the value of delta H, more will be sigma 1, and by that curve will shift like this. So here I am able to observe a very important phenomena, that larger is the value of sigma 1, see the neutral plane is shifting towards exit. Okay, na? Now, for a particular value of delta H, larger the value of delta H, more will be the value of sigma 1, and my neutral plane will keep on shifting in the right, towards the exit. For a particular value of delta H, it will so happen that neutral plane will coincide with the vertical axis. Neutral plane will coincide over the vertical axis. If it so happens, there is no backward slip. Once the neutral plane coincides with the vertical axis, there is no backward slips. So at this point, what is happening? Roll is slipping over the work without any deformation. Roll is slipping over the work without any deformation. So beyond that condition, I cannot roll the material. Beyond that condition, I cannot roll the material, and the bite angle at rolling limit, bite angle at the rolling limit is called angle of nip. Angle of nip is nothing but 2 mu radians. Angle of nip is equals to 2 mu radians. So beyond a certain value, it is not possible to give deformation, or it is not possible to roll any material, and that maximum deformation bite angle is called angle of nip. Is that all right with everyone? So it was a very, very important concept. So I told you, to you look approximately for 45 minutes. Up to this point, you have to study very, very carefully. Some of you might have studied these things first time, so you have to see little carefully. Now, suppose there are two rolls. There are two rolls. Another very, very important point. To give this much amount of deformation, let us say R1 is the roll radius. And this is the friction hill. And the area of this friction hill will give me the rolling load. Area of this friction hill will give me the rolling load. But let us say same amount of deformation delta H, is carried out using smaller diameter rolls. R2 is smaller diameter rolls. When the same amount of deformation is carried out by smaller diameter rolls, there is no change in H2 and H1, but there is a change in the roll radius. Then the friction hill will be like this. Friction hill will be like this. So what I am able to observe from here, very, very important thing. Please look at it very carefully. If you understand this, Lot of theoretical questions from the rolling you can handle very, very easily. For giving the same amount of reduction, when I am using smaller and smaller diameter rolls, area of the friction hill keeps on decreasing. So smaller is the radius of roll, lesser will be rolling force. Lesser will be rolling force. Lesser will be rolling force. So it is good, na? I am giving the same amount of reduction. Lesser energy will be consumed by a smaller radius rolls. So I will use a smaller radius rolls. But by using a smaller radius rolls, there will be a problem. Suppose these are all. See my hand, it is a roll. And when I'm using a smaller radius roll, although the roll separating force is decreasing, but that roll separating force is sufficient to bend the roll. So during rolling, roll will be bended like this. And when the roll gets bended, the cross-section area will not be uniform. Outgoing rolled materials area will not be uniform. Okay, na? So how to handle this problem? Because ultimately I want that lesser and lesser energy should be consumed in rolling the material. So there are two methods. One is using camber roll. For this problem, what is the problem? I want to use lesser energy to deform the material, but simultaneously rolls are getting deformed. So camber rolls, and the second is a 4 high mill. Okay. Now camber roll is, I will make the roll in the form of a mridanga in South India. Most of you may be South India. So mridanga. I will use these type of rolls. These are called camber rolls. Camber rolls are sometimes called convex rolls, sometimes called convex roll. And this is the camber. So what happens when you start rolling it? Camber will shift on the other side and your outgoing cross-section area will be uniform. And when you stop rolling, camber rolls will regain its shape because these roll deformations are in the elastic limit. These roll deformations are within the elastic limit. Camber rolls deformations are within the elastic limit. So see, if it is live, if there is any doubt and all that, I could have clarified, because in rolling section, a student gets many small doubts. So unfortunately it is not live, it is recorded one, but still I will keep on seeing the chat box and channel, Telegram channel. So I will be taking care of it, don't worry. But these camber rolls or convex rolls It is also called convex rolls. Convex rolls are used only in the mass production. Camber rolls or convex rolls are produced only in the mass production because either you change delta H, or you change material, you need a separate set of camber rolls. So camber rolls are used only in the mass production. Second method is a 4-high mill. 4-high mill. So what is a 4-high mill? Deformation is carried out by smaller diameter rolls like this. Basically, I'm giving the deformation by using the smaller diameter rolls. And on the back side, there are large diameter rolls. On the back side, there are large diameter rolls. Power is given to the smaller rolls. These large diameter rolls are also called back rolls. Large diameter rolls are called back rolls. Power is not given to the large diameter rolls because large diameter rolls, they are in contact with the smaller diameter rolls. So if the smaller diameter rolls wants to deform, large diameter rolls will say, wait a minute, I am there, you don't deform. Like a big brother, a small brother is fighting, big brother is standing behind him. Suppose the small brother wants, he's about to fall, he will support. Don't worry, I'm there. Like main hu na, I'm there, don't worry. Okay, na? So, large backup rolls prevent the deformation of smaller diameter rolls. Now, there is a very, very important point. 4-high mills are also used. 4-high mills are also used to give deformation in a certain range of delta H value. Okay? Because by the change in the delta H, here very, very carefully, by the change in the delta H value, position of neutral plane will change. By change in the delta H value, position of neutral plane will change. So the direction in which the maximum roll separating force appearing will also change. The direction in which the maximum roll separating force appearing, that is also change. So let us say if it appears in this direction or this direction, that direction backup roll may not be there. So 4-high mills are used to give deformation in a certain range of delta H value. So now in my application, let us say delta H changes drastically. For that, I use cluster mill. Cluster mills also called 𝐶𝐚𝐴 mill. Cluster mills are also called 𝐶𝐚𝐴 mill. Now the PPT is available to all of you. The power is given to the smaller rolls. But there are so many back rolls, 1, 2, 3, 4, 5, 6, 7, 8, 9. Both sides, there are many, many rolls. So now, the 𝐶𝐚𝐴 rolls are also called universal mills. Because from any direction and any delta H can be given, deformation can be given to the material, because there are many backup rolls. So wherever the smaller rolls tries to deform, some backup roll is always there. So St-Smear mills or cluster mills are also called universal mills. Okay, na? Next is planetary mill. Planetary mill. Now, around 15 minutes before I explain to you, 15 minutes before I explain to you, that there is something called rolling limit. And the nip angle is nothing but 2 mu radians. Now, planetary mill, we have tinkered with this concept. In the planetary mill, simultaneously multiple pair of rolls are engaged in deformation. See, first pair, second pair, third pair. Power is given to the larger roll. Power is given to the larger roll, and these smaller rolls are connected to the surface of larger rolls through individual axle. Through individual axle. Power is given to the larger roll. So, because multiple pair of rolls are engaged in the deformation simultaneously, this increases the rolling limit. So in the planetary mill, a thick plate can be converted into thin foil. Thick plate can be converted into thin foil in one go. Can be converted into thin foil in one go. Like aluminum foil. Aluminum foil is produced by pack rolling. Aluminum foil is produced by pack rolling. What is a pack rolling? 2 layers of sheet, roll it together. Once it becomes foil, after rolling you separate it out. This portion will be rough and this portion will be shiny. So intentionally the aluminum foil, one surface is kept rough and another surface is kept shiny. And foils are produced by planetary mill. Foils are produced by planetary mill. Suppose this is the rolling operation. If you see the plan, then how the rolling setup looks like. How the rolling setup looks like. So rolls are given rotation. This is the incoming material. Incoming material. W1 is the width. And during deformation, what happens? See, the outgoing material will be like this. It's a outgoing material. So if you take the mean, W2 is the width of outgoing material, and these are the wavy edges, VV edges. W2 will be more than W1, and W2 minus W1 is called spread. So in the question, if the spread is given to you, you have to find out W1 plus W2 by 2. So in the force calculation, sigma naught L into W, this W should be W mean. If the spread is given to you, it should be W mean. And this wavy edges and spread are due to anisotropy of the material. Are due to anisotropy of the material. Wavy edges and spread is due to anisotropy of the material. Okay, in the crash course, I have gone through quantification of anisotropy, but here the one-shot lectures, the target is that in 4 hours, we have to complete everything. So that thing I am not discussing here. So generally after rolling, it is a sheet. After rolling, generally it's a sheet. Okay? After rolling, generally it is a sheet. Okay? So in the sheet metal forming, there are certain very, very important things. So we are going to go through it. Very, very important things. Sheet metal. There are very, very important things in the sheet metal. Suppose this is the die. And over the die, we are keeping a sheet blank. This is the blank holder. This is called blank holder. We are applying pressure on the blank holder. And this is the punch. And between the punch and the die, there is a clearance. Punch and the die, there is a clearance. So when the pressure, a blank holding pressure is sufficient, so that it is not allowing the sheet to slip between the blank holder and the die, there will be shearing. There will be shearing. So when the removed material is useful, it is called blanking. And when the removed material is a waste, it is called punching. Punching is also called piercing. But technically there is slight difference between piercing and punching, but in GATE exam you can take it same. Piercing, there is no material removal. Suppose you are firing a bullet on a sheet, so the metal will go other side, no material removal. That is technically called piercing. Punching means there is a metal removal. Punching and blanking. You please mug up this thing. Punching, punch is exact. In punching, punch is exact. Clearance will be on the die. And the blanking, die is exact. Clearance will be over the punch. And from the geometry we can say that punch will always be smaller than the die. Punch will always be smaller than the die. Please remember this thing. For example, from a 2 millimeter thick sheet, I want to cut 30 millimeter blank. Let us say clearance is 3%. What is the dia of punch and die? What is the dia of punch and die? So these type of question appears in GATE, okay na? Now it's a blanking operation. It's a blanking operation, and blanking the die is exact. So die will be exactly equal to the diameter that you want to cut. Diameter you want to cut. Clearance will be on the punch, and the punch will be smaller, minus clearance. So clearance is on both the side, na? See clearance on this side. So clearance is on both the side. So minus 2 times clearance is 3%. And clearance, if the clearance percentage is given to you, it is always percentage of sheet thickness. It is always percentage of sheet thickness. So comes out to be 29.88 mm. This should be the size of punch, and this should be the size of die. Punching, punch is exact. Clearance will be on the die. In the blanking, die is exact. Clearance will be on the punch. Now suppose question says that I want to create 30 millimeter hole. In the sheet, I want to create 30 millimeter hole. Suppose the question is like this. So such type of question you have to read very, very properly. Question is asking about punching or blanking. That you should be very clear. So now it's a punching operation. If you want to create 30 millimeter diameter hole, it's a punching operation. So size of punch will be 30 mm, because in the punching, punch is exact. Die will be bigger than the punch. So dimension of die will be 30 plus clearance, same clearance. 2 into 30 by 100 into 2, same clearance on the die. So that will be 30.12 mm. Please remember this. For GATE it is important. In punching, punch is exact, and in blanking, die is exact, and the other thing we will give the clearance. Okay na? Now there is another very important concept called shear. Shear. Suppose the punch is like this. This is a punch, na? If I chamfer a little bit here, so punch comes in this shape. This is called a shear. This is called shear. When there is no shear, load displacement curve will be like this. No shear. And with shear, punch displacement curve will be like this. With shear. So you know why we provide shear? Here very, very carefully. Why we provide shear? Why we provide shear? To decrease the maximum load on the punching machine. Decrease the maximum punching load on the machine, but that load will be there for longer period of time. Shear decrease the machine capacity. Shear decrease the machine capacity. That is the first point. Second point is energy consumed to shear the material. Energy consumed to shear the material will be same with or without shear. So work done is the force. How much force is coming? Multiplied by penetration. So how to calculate force? Yield strength in shear multiplied by shear area. Multiplied by shear area. Multiplied by penetration will be the work done. With shear, work done will be F max penetration plus shear. Penetration plus shear. Okay? But remember one thing here also. If the shear is more than thickness of sheet, then work done will be F max into shear. Penetration will not come into picture. Once again, 2 points. Point number 1, shear is provided to decrease the machine capacity, but that maximum load on the machine will be there for longer period of time if there is a shear. And the second concept is work done with or without shear will be same. Work done with or without shear will be same. But here there is a catch. If the shear is provided on cylindrical punch and dies. Cylindrical punch and dies, na? Punch and die. Cylindrical punch and die, this is the shear. Then I want you to mug up one formula. This maximum punch load with shear is nothing but K dash pi dt. D is the diameter of the punch. Penetration divided by shear. Penetration divided by shear. T is the thickness of sheet. T is the thickness of sheet. So in the blanking and punching, if there is a shear, it decreases the machine capacity. Okay, na? There is one more very beautiful thing. In the same setup, if you see, sheet, blank holder, punch. Point number 1, there is no shear. In place of shear, there is a curvature. This curvature is 5 to 6 times the sheet thickness. This curvature is 10 to 12 times the sheet thickness. Point number 1, there is a curvature, no shear here. This blank holding pressure is 2% of the yield strength of the material. 2% of the yield strength of material. And this clearance is approximately 1.2 times the sheet thickness. Clearance is approximately 1.2 times the sheet thickness. Under these conditions, sheet will slip between the blank holder and the die and come out in the form of a cup. And this process is called deep drawing. And the process is called deep drawing. You know, because it's a GATE 2023, those students, those who are hearing this lecture after that, because it will be throughout on the YouTube, for forming, you can follow my book, because I have worked very hard for metal forming chapter and metallurgy chapter. Narosa will publish it, and I'm telling them, it's the 4th edition. I'm telling them that during GATE exam and at least up to GATE result, he should put in the market both industrial and my production books to Narosa publication, Delhi. So I have put a lot of effort in metal forming and metallurgy chapters. Other chapters were easy because these 2 chapters, stuff is not available, especially so that students are satisfied, those who are preparing for competitive examinations. So this is called deep drawing. Okay. Now, D is the diameter of blank. It is converted into a cup-shaped component. A small d is the diameter and h is the height. Diameter d by small d is called draw ratio. It is called draw ratio. When we increase the blank diameter, capital D is the blank diameter. When you keep on increasing the blank diameter, height will keep on increasing. But remember one thing, this is called punch corner region. This is called punch corner region, and the maximum load punch is applying in this region only. Maximum load punch is applying in this region only. So if you see the cross section, there will be a neck. There will be a neck. Because punch is applying the maximum load in this region. Increasing the diameter, more will be this neck. More will be this neck. And when the diameter exceeds beyond a certain value, there will be fracture. There will be fracture. So here we define a term called limiting draw ratio. Limiting draw ratio, LDR. It is the maximum diameter safely we can draw. Maximum diameter safely we can draw divided by the cup diameter is called limiting draw ratio. And limiting draw ratio tells you the formability of the material. Formability of material will be more when the work hardening exponent is more and anisotropy value R bar is more. And up to certain thickness of the work material is more. But these two plays a very, very important role in defining the formability of any material: work hardening exponent and the normal anisotropy R bar. Larger is the diameter, more force will be required, so neck will be more. Now, this diameter converting into this cup, please see very, very carefully what I am doing. In actual GATE exam, they will ask you some unknown, either blank diameter or cup diameter or the cup height. Generally, because GATE exam already there is a time crisis, so you do that by equating the surface area. Equating surface area. So pi by 4 d square is equals to pi by 4 d square plus pi dh, and generally by that you will get the answer in actual GATE exam. But some of the people, those who design test series, they want to confuse the students. It is not for the welfare of a student, but they want to confuse to show them that they know something. You know what they will do? Whatever option available, there will be very slight difference. 25.01, 24.98, 24.96, 25.023. There will be very slight difference. If that is the case, because you will be attempting different test series, if that is the case, it means you know what the person who set the test series, what is expecting. Equate the volume. Equate the volume. So how to equate the volume? Pi by 4 d square, t is the sheet thickness. Okay. Now here, pi by 4 d plus 2t square into t. You know, whatever geometry is given, I'm just equating the volume. So this is the volume of this. Now, what is the volume of this? D plus t plus pi d h 2 pi r h into t. I'm just equating the volume. So see, whatever the geometry is given, if you get the volume, this answer will come. But generally for GATE already, because this calculation will be little complex. In the GATE with the option, all the option, there is a good amount of difference. Just equate the area, you will get the answer. If there is a fractions difference, generally I have seen this question in the test series. Equate the volume. In 𝐂𝐴𝐺, he equates volume. That's the reason these test series have gotten that idea from there. Okay. So please don't forget that one. This blank At some intermediate stage, it will be this, and final it will be a cup. Final, if it will be a cup. This is called flange region. This is called cup wall region, and this is called cup bottom. Different parts. In the cup bottom, there are no stresses. There are no stresses on the cup bottom. So here also in the gate, sometime these questions appear. That's the reason I am hitting it. At the cup bottom, there are no stresses. In the cup wall, uniaxial stretching. Because I am pulling the material in the cup wall, uniaxial stretching. And in the flange region, if you see the plan, take the element here. So one stress will be acting in this direction. Like the paper. Suppose if you take a paper, apply force. The paper folds, na? Paper folds. So there will be some compressive hoop stresses and radial tensile stresses. So in the flange region, there will be radial tensile stresses and compressive hoop stresses. Because there are compressive hoop stresses, sheet will try to fold. And if you do not apply blank holding pressure, there will be wrinkling. If you do not apply compressive stress, there will be wrinkling on the cup wall. It's a defect in the deep drawing, wrinkling. And if the work material is having a coarse grain structure, after forming, the drawn cup will have very rough surface. Like the orange, na? Orange, if you peel, inside surface how it looks like, very rough. When it will happen? When the work material is having a coarse grained structure. And this defect is called orange peel. This defect is called orange peel. You know, of course, it's a one-shot crash course, one shot. That's the reason I'm discussing only the important concept. So, but in the regular crash course, that was in English, I have gone little deep into it. So deep drawing, punching, blanking. Under certain circumstances, the sheet will come out in the cup form. Deep drawing. But there is a limit up to which we can deep draw. Beyond that, there will be fracture. Some of the defects are like orange peeling, crack, wrinkling. Why? Because there are different stresses in the different regions of the drawn cup. Different stresses in the different regions of the drawn cup. Along with GATE, there are other PSC's exams, because today, when I'm recording this, BPSC assistant professor result came, and my mail was flooded. Basically, many students of mine are selected in BPSC, and they are sending thank you very much. But my nature is not to publicize, okay, na? But I am grateful to students and my teachers so that I can guide all of you. Okay, na? So in the PSCs, one question appeared very frequently from this gate, from this particular section. Single action press, double action and triple action. Single action presses only when the top ram is moving. Single action press. Either this ram moves or this ram moves. It's a single action press. Double action press is when both the rams move like this. Here, independently, both the rams, top ram and bottom rams are moving. It is called double action press. Now the triple action presses are used. Triple action presses are used in deep drawing. You know how? Once the punch goes down, suppose this is your punch. Punch goes down, cup will stick to it. Cup will have some thickness, huh? Cup will stick to it. Now there is something called stripper plate. Stripper plate. So when the punch is moving in the backward direction, this is the third action. So the cup will hit the stripper plate and the cup will fall down. Third action, cup will hit the stripper plate and the cup will go down. So to remove the cup from the punch, so third action is used to remove cup from punch. To remove cup from punch. So the triple action or three action presses are used in deep drawing. So this question I have seen many times, so that is the reason I thought of covering here, because English speaking Indians, or maybe because in the crash course some students are from Bangladesh, Nepal and Pakistan are also joining. You know, as a student I love all of you. Doesn't mean that actually, you know, because you are from other part of India, apart from India, then we don't tell you, we teach you. And whatever question that are there, you are welcome to ask through Telegram channel of PW. So other course, whatever I have taken, I have seen Bangladesh, Nepal, and Pakistan also some students were there. Okay, na? So now let us do some questions. These are very easy questions. These are very easy questions. So just please read it first before we hit it. Please read the question before we can hit. Okay. So as I told you, we will write all the data on the diagram. We will write the entire data on the diagram. 42 millimeter thick plate. 42 millimeter thick plate is made of low carbon steel, is to be reduced to 34 millimeter. 34 millimeter in one pass in the rolling operation. As the thickness is reduced, the plate widens by 4%, meaning W2 is 1.04 widens by 4%. So W2 is 1.04 times W1. The yield strength of the steel plate is 174 MPa and the ultimate tensile strength is 290 MPa. The entrance speed of the plate is 15 meters per minute. 15 meters per minute. And the roll radius is 325 millimeter. 325 mm. The rotational speed is 4.9 rpm. Okay, na? Determine the coefficient of friction for maximum draft, exit velocity, and the slip. I think because the question is such that you don't require these things. So that is the reason I have not written the data. Mu V2 and slip. Mu V2 and the slip you have to find out. So all the data is written on the board. So mu is equal to delta H is equal to mu square R. That's what we have proven. So delta H is nothing but 42 minus 34. R is given, so find out mu. You can find out mu. So I hope you have calculator and pen and paper with you so that you can do the things along with me. My answer is 0.157. 0.157. Now to V2, apply continuity equation. V1 H1 W1 is equals to V2 H2 W2. Correct, na? Continuity equation because width is different. So 15 H1 is 42. W1 is equals to V2. H2 is 34. W2 is 1.04 W1. What I have done? Continuity equation. So V2 is 17.8 meters per minute. .8 meters per minute. A radius and RPM are given to you. So roll velocity is nothing but velocity of neutral plane. So 2 pi r n, because these are meters per minute. So I'm not dividing by 60 because 60 will make you meters per second. Okay, 2 pi r n comes out to be 10 meters per minute. 10 meters per minute. Because it is a millimeter, divide by 1000. Because millimeter has to be converted into meter. So divide by 1000. So forward slip is V2 minus VR divided by VR into 100 will give you the forward slip. So just calculate the answer for the answer comes out to be 78%. I hope most of you are, those who are seeing the recording, answer will be same. Yeah. A series of cold rolling operations are to be used to reduce the thickness of plate from, there is no gap, so just I'm drawing here. Thickness from 50 to 25. Series, not one step, multiple steps. Okay, na? Diameter is 700 mm. Diameter is 700 mm. Mu is equals to 0.15. Now, what is the draft for each pass? Delta H is equals to mu square R. So 0.15 square into R is 350. So delta H for each pass you can calculate from there, and it is 7.87. There is a draft of each pass. It's a very simple problem. Number of passes, overall draft, how much is? 25. Overall draft is 50 minus 25 is 25. Divided by 7.87. 3.17. So 4 passes. Because even if it is 3.1, I will do 4, because from where I will get this 0.1. So total 4 passes will be required. Total 4 passes will be required. See this one? See this one? I hope there will be a space. Yeah, space is there. $250 millimeter wide and 25 millimeter thick. 250 millimeter wide and 25 millimeter thick is to be reduced in a single pass in a too high rolling mill to a thickness of 20 mm. Thickness of 20 mm. The roll has a radius of 500. Roll has a radius of 500. And its speed is 30 meters per minute. It's a roll speed. The work material has a 240 and 0.2. Find the roll force, torque, and power. Force, torque, and power. This is the data. So pretty much you should focus on the same procedure. Write the data and then solve it. Okay. So force is sigma naught L into W. So sigma naught will be the mean. K epsilon raised to power n over n plus 1. And epsilon we calculate always the direction in which the load is applied. So epsilon is nothing but ln h1 by hf. Put it here, you will get sigma naught. Do it along with me. Do it along with me. It should be 148.1 MPa. 148.1 MPa. Generally, if it is a live, I could have taken some time so that answer comes from you. Okay, but presently I'm recording and is only screen is in front of me. It is difficult to teach screen, but if it is live, there's a different mechanism between teacher and students. Okay, anyway, and L under root R delta H, and W is already given. Find out what is force. What is force? (1851 kilonewton). 1851 kilonewton. Torque will be F into L by 2, and this L, my answer is 50 mm. My answer was 50 mm. So torque is 46.28 kilonewton meter. 46.28 kilonewton meter. Power. See, this thing we have calculated per roll. This we have calculated per roll. So power will be torque into omega 2 times, because I have to calculate omega is 2 pi n by 60, correct, na? From here you can calculate an pi dn and put it here. You will get the power 92.5 kilowatts. 92.5 kilowatts. Anyway, okay. It's a same question, same type of question, because previously I have shown you how to do it and it's a recorded one. I will give you the answer. There is no change. Similar to the last problem, we have to follow the same steps, but answer is asking in horsepower. It's a 277 horsepower. So best way, you pause the video and then solve it and match the answer, then you move forward. Okay, so in the one shot series, that is the best way. If you want to learn something additional, fast forward, reverse, pause, that options are available with you. Okay, that options are available with you. Okay, so I'm giving the answer of this one. A 10 millimeter thick plate is rolled to 7 millimeter thick. In rolling mill using 1000 millimeter diameter rigid rolls. Question is telling theta is the bite angle, theta neutral plane. The neutral point is located at an angle 0.3 times to that of bite angle, means theta n is 0.3 theta. Okay. The thickness is millimeter up to 2 decimal places at the neutral point. This is H1, H2, this is Hn. This is HN. Okay. So HN, we have to calculate HN. We have to calculate HN. So the theta, you can calculate theta because tan theta is equals to mu, na? So the theta, my answer is coming out to be 4.43 degrees. So 0.3 times theta is theta n. So theta n is 1.32. I think up to this point you don't have any problem. Up to this point you don't have any problem. Okay. Now this triangle OAB, OAB, theta n. Calculate this OB. Like, I will make little bigger diagram. This is the theta n. Okay. And you have to find out what is this HN. And this is your H2. O, A, B, C. So HN will be H2 plus 2BC. Correct, na? H2 plus 2BC. So this is R, and this BC is nothing but radius minus OB. Is radius minus OB is BC, and the OB is nothing but R cos theta n. You got R, you got theta n, put it here. OB will get OB, put it here, BC, you will get HN. So it's an intermediate question. That is the reason I told you the way I have derived in the beginning of lecture. The way I have derived in the beginning of lecture, if you follow that, it will be easy. So get the answer. I am having the answer of HN. I am having the answer of HN. It is 7.29, 7.27 mm. 7.27 mm is that height. At the neutral plane, that is the height, 7.27 yum. So, you know, why I have included this problem in one shot? That always don't mug up the formula. Don't mug up the formula always. See the procedure with which we derived all these things. Okay, na? See the procedure. Question is asking about the bite angle. Delta H is equals to mu square R. Delta H is equals to mu square R. So it's 0.01 R. This is delta H by 2. A, B, C. Can I say cos theta is nothing but AC by AB? AC by AB. And AC is R minus delta H by 2 divided by R. So 1 minus delta H by 2R, and delta H is here, 0.01 R divided by 2R. R cancel out. Take the inverse. You will get the bite angle by this procedure. You will get the bite angle by this procedure. So I think it's a P by Q. This particular question is a P by Q. Previous question we have framed, our team has framed, and this particular question is a P by Q. And this answer, my answer is coming 5.76 degree. Because I have already calculated, so there may be some error. But anyway, I don't have percentage calculator, but that is the way it will go. Okay, it's simple mathematics. Rolling problems is a simple mathematics. It's a blanking operation. Blanking die is exact, so die will be 50 mm. Okay, die will be 50 mm. So these options cannot be correct. Punch will be smaller. 50 minus 2 times the shear. It's a 6%. 6% of the sheet thickness. Okay. I think this is the answer, B. Just check it once. That's the answer. This answer. It's an easy one. So that finishes my course on one-shot course on metal forming. Once again, these courses are designed around 4 hours. We can consolidate it each and every topic. So material science, metallurgy, and forming. Next is casting. Thank you very much. If there is any question, please contact me through the chat, PW Telegram chat, Telegram box. Okay, na? Thank you very much.